into, well, an unseen world where light meets matter.
It's a place full of quantum surprises, really.
Exactly. Forget what you thought you knew about electrons just, sitting there. We're about to witness this really complex, delicate quantum dance.
Yeah, a dance where a single photon, one tiny bit of light, can make an electron do one of two completely different things.
Right. One is super dramatic, kicks the electron right out of its home. That's the photoelectric effect.
And the other. It's incredibly subtle. The electron stays put, basically, but its internal compass, its magnetic moment, just flips, reorients itself.
So our mission today, our deep dive, is to look at these side by side. Not just how they happen, but why they're so different.
What rules they follow and how these fundamental differences led to technologies that, well, really shape our world. We want to compare them directly.
Okay, let's start with the electron itself. Beyond charge and mass, it has this intrinsic property, spin. But when we say spin, it's not actually spinning like a top, is it?
No, not at all. That's just an analogy. It's purely a quantum mechanical property. Think of it as built-in angular momentum.
And it only has two options.
Only two. We call them spin up and spin down. That's it. It's a consequence of its spin quantum number, which is 1/2.
And this spin, because the electron also has charge, means it acts like a tiny magnet.
Precisely. It has an intrinsic magnetic dipole moment. It's like a tiny, tiny bar magnet embedded within it.
And there's that weird quantum thing, the G factor.
Ah, yes. The G factor tells you how strong that magnet is relative to its spin. Classically, you'd expect it to be 1, but for an electron, it's actually about 2. Well, slightly more, about 2.00232.
Twice as strong as you'd think.
Pretty much. And because the electron's charge is negative, the magnet points opposite to the direction of the spin. This magnetic moment is key. Is the electron's handle for interacting with magnetic fields.
And we know this isn't just theory. There was experimental proof.
Oh, definitely. The Stern-Gerlach experiment back in 1922. Classic stuff. They shot silver atoms, which have one unpaired electron through a non-uniform magnetic field.
And classically, you just expect a smudge on the detector screen, right? A continuous spread.
Exactly. But what they saw was the beam splitting into two distinct spots. Two.
Wow. Direct proof.
Direct proof that the electron's magnetic moment tied to its spin is quantized. Only two possible orientations in the field. Must have been mind-blowing at the time.
Okay, so electrons aren't just floating free. They live in specific energy environments. First, there are bound states. What's that mean?
Bound states are when electrons are trapped, essentially, confined within an atom, like in atomic orbitals, or within the structure of a solid material in energy bands.
And their energies are specific, like steps on a ladder.
Exactly. Quantized energy levels and the spin flip we mentioned. That happens to an electron in one of these bound states. It stays bound.
But then there's a free state continuum.
Yeah.
Sounds liberating.
It is. That's when an electron isn't bound to anything. It can have any amount of kinetic energy above zero, a continuous range. It's free to roam.
And the photoelectric effect is what bridges these two.
Precisely. It takes an electron from a bound state and kicks it right out into that free continuum. Sets it free from the atom or material.
So this leads to a really core distinction, doesn't it? How the photon interacts.
Absolutely fundamental. For the photoelectric effect, it's the photon's electric field interacting mainly with the electron's charge.
Like an electric push.
Yeah. But for the spin flip, it's the photon's magnetic field component interacting with the electron's magnetic moment, especially when you add an external magnetic field. Different handles for different jobs.
Okay, let's dig into the photoelectric effect first. The electron kicking one. Classical physics had real trouble here, right?
Big trouble. Wave theory couldn't explain why you needed light of a certain minimum frequency, a threshold frequency, to get any electrons out.
Intensity didn't matter below that threshold.
Nope. Didn't matter how bright the light was. And it couldn't explain why the electrons came out instantly once you hit that frequency.
So classical waves predicted what? More intensity should always mean more energy transfer.
Yeah, it suggested that if you just shone a dim light long enough, eventually an electron should absorb enough energy to escape. But that's not what happens.
Enter Einstein in 1905.
Right, with his radical idea. Light isn't just a wave, it comes in packets. Quanta, photons.
And the energy of each photon depends only on its frequency. E equals hf.
Exactly. E is energy, H is Planck's constant, S is frequency. That equation changed everything. Suddenly, the frequency threshold made sense.
Because you need a single photon with enough energy to overcome the work function?
Precisely. The work function, usually written as eta phi, is that minimum energy needed to pry an electron loose from a specific material. It's like an exit fee.
Different materials have different fees.
Yep. Alkali metals, like sodium or potassium, have low work functions. They let go of electrons easily, even with visible light. Other metals, like zinc or copper, hold on tighter, need higher energy UV light.
And it's strictly one photon to one electron.
One photon interacts with one electron, all or nothing. If the photon's energy, HF, is less than the work function, the electron stays put. Doesn't matter how many photons arrive.
Like you said, ping pong balls versus a bowling ball.
Exactly. You need that single impact with enough energy.
Which gives us the photoelectric equation. The maximum kinetic energy, Kmax, of the electron that gets out is just the photon's energy minus that work function. Kmax equals HF.
That's it. The leftover energy becomes the electron's kinetic energy, how fast it's moving after escaping.
And the intensity of the light. Brighter light just means
more photons per second. So more electrons get kicked out per second, assuming HF is above the threshold. But each electron still has the same maximum kinetic energy because that only depends on the frequency.
such a crucial point. And the interaction itself, you said, is mostly the photon's electric field and the electron's charge.
Right, an electric dipole transition. And it follows specific quantum rules, selection rules. The electron's orbital angular momentum, its Elec quantum number, has to change, usually by 1.
And something called parity has to change, too.
Yes. The symmetry of the electron's wave function has to flip. It's a fundamental requirement for this kind of transition.
But importantly, the electron's spin doesn't change.
Correct. Spin is conserved in the photoelectric effect. An upspin electron comes out as an upspin electron.
And after the electron leaves, the atom is ionized, left with a positive charge.
Yes. And that process can reverse, actually. A free electron can get recaptured by an ion, emitting a photon. That's called radiative recombination. It's how LEDs work, basically.
Okay, fascinating. Now let's switch gears completely. Spin flips. You said normally spin up and spin down have the same energy. Degenerate.
That's right. In the absence of a magnetic field, there's no energy difference between them. An electron doesn't prefer one spin state over the other energetically.
So to make a flip possible, to make it mean something in terms of energy you
need to break that degeneracy.
Yeah.
You need to make one state slightly higher energy than the other.
How do you do that?
Apply an external static magnetic field. Let's call it B euro.
Ah, so the electron's tiny internal magnet interacts with this big external magnet.
Exactly. That interaction causes the energy levels to split. The spin aligned with the field goes slightly lower in energy, the one opposed goes slightly higher. This splitting is the Zeeman effect.
And the size of that energy split, the one depends on the strength of the external field.
Directly proportional. Stronger field, bigger split. E equals gyro, B euro. Where G is that electron G factor, euro is a constant called the Bohr magneton, and B is the magnetic field strength. The key is it's tunable. You control the gap.
So you've created the specific energy gap. Now, how do you get the spin to flip across it?
You need a photon whose energy, HF, exactly matches that gap.
Resonance.
Perfect resonance.
Yeah.
HF to HF. If the photon's energy is even slightly off, nothing happens. It's incredibly selective.
And because that Zeeman splitting is usually quite small.
The photons needed are low energy, typically microwaves or radio waves, much, much lower energy than for the photoelectric effect. We're talking microelectron volts or millielectron volts compared to electron volts or kilo-electron volts.
Well, like for a typical lab magnet, maybe 0.3 Tesla or so?
Yeah, for about 0.34 Tesla, the resonance frequency is around 9.5 gigahertz. That's firmly in the microwave band.
And the interaction mechanism here is different, too. It's the photon's magnetic field component talking to the electron's magnetic moment.
Yes, a magnetic dipole transition. This is crucial. Electric dipole transitions, like in the photoelectric effect, are generally much, much stronger than magnetic dipole transitions.
So this magnetic interaction is weaker, more subtle.
Much weaker, by orders of magnitude. That's another reason why resonance is so critical. You need that perfect energy match for this relatively weak interaction to have a noticeable effect, to actually induce the flip. It's like trying to push a swing. You get the best result if you push exactly in time with its natural frequency.
It really highlights the different ways light can interact, doesn't it? And the selection rules for spin flips must be different, too.
Completely different, almost the opposite in some ways. For a spin flip, the magnetic spin quantum number, EMS, must change by 1. That is a flip, by definition.
But its orbital state
Stays the same. Orbital angular momentum is conserved. The electron flips its spin but stays in the same orbital neighborhood.
and parity.
Also conserved. The spatial symmetry of the wave function doesn't change. Contrast that sharply with the photoelectric effect. where parity had to flip.
So after the photon causes the flip, the electron is in a higher energy spin state, but it's still bound.
Still bound. It's in an excited state, but the atom isn't ionized.
And how does it get back down to the lower energy state? Does it spit out another microwave photon?
Usually not. It typically relaxes back down through non-radiative processes. It interacts with its surrounding environment, the lattice in a solid, or other nearby spins.
Ah, the relaxation processes, T1 and T2.
Exactly. Spin lattice, T1, and spin-spin, T2 relaxation. Essentially, the excess energy from the spin flip gets dissipated as heat, tiny vibrations in the material, rather than being emitted as another photon.
So it just warms things up a tiny bit.
That's a good way to put it.
Okay.
The energy leaks away into the environment.
Okay, we've looked at them individually, but putting them side by side really makes the differences stark.
It really does. Let's recap the core dichotomies.
First, the nature of the transition itself. Photoelectric effect is.
Bound to free, electron ejected, system ionized.
And spin flip.
Bound to bound, electron stays put, just flips its spin. System excited, but neutral.
Photon energy required.
High energy for photoelectric UV X-rays. Think EV to cave. Very low energy for spin flips, microwaves, radio waves, micro-EV to milli-EV range. Orders of magnitude difference.
Interaction type.
Photoelectric. Strong electric dipole. Photons E field plus electrons charge. Spin flip. Much weaker magnetic dipole. Photons B field plus electrons magnetic moment.
The condition needed.
Photoelectric.
Yeah.
Energy threshold. H8 must be greater than the work function. Spin flip. Precise resonance. Spin flip must exactly equal the Zeeman splitting E.
Selection rules.
Almost opposite. Photoelectric needs L1, parity change, but conserves spin. Spin flip needs L's whip, conserves L, conserves parity.
Dependency.
Photoelectric depends on an intrinsic material property, the work function. Fixed for that material. Spin flip depends on an external factor, the applied magnetic field. You can tune it.
And what happens afterwards?
Photoelectric leads to ionization. Return to ground state can involve photon emission via recombination. Spin flip leads to an excited bound state. Returns to ground state via non-radiative relaxation dissipates as heat. No photon out, usually.
Wow, when you lay it out like that, they really are fundamentally different ways for light and matter to interact at the quantum level.
Absolutely. Different mechanisms, different rules, different energy scales, different outcomes.
And these deep differences lead to completely different technologies. Let's talk applications. From the photoelectric effect, kicking electrons out, what do we get?
Well, the big one is photovoltaics, solar cells.
Right. Sunlight hits the semiconductor material.
Knocks electrons loose, creating electron-hole pairs that's like an internal photoelectric effect. And built-in electric field then separates these charges, driving a current, light into electricity.
Makes sense. What else?
Photodetectors. The sensors in your digital camera, CCD, CMOS sensors. Light hits a pixel, generates photoelectrons.
Which build up a charge.
Exactly. The amount of charge tells you how bright the light was, that pixel.
Yeah.
That's how you build a digital image. Every digital photo relies on this.
And there's a scientific technique too, XPS.
Ah, yes, X-ray photoelectron spectroscopy. Very powerful. You hit a sample surface with X-rays of a known energy. These X-rays knock out core electrons via the photoelectric effect. You then carefully measure the kinetic energy of these ejected electrons.
And because you know the X-ray energy, OTHF, and you measure the kinetic energy, Kmax.
You can calculate the electron's original binding energy using E-binding equals HF Kmax. Since each element has unique core electron binding energies, you can tell exactly what elements are present on the surface and even a bit about their chemical state. It's like chemical fingerprinting.
Okay, so that's electron ejection. What about manipulating spin? Technologies from spin flips.
The most direct application is electron paramagnetic resonance spectroscopy, EPR, sometimes called ESR, electron spin resonance.
What's that used for?
It specifically detects and studies molecules or materials that have unpaired electrons. Things like free radicals, many transition metal complexes, defects in solids.
How does it work? You put the sample in a magnetic field?
Exactly. Apply a magnetic field, sweep the frequency of microwaves, and look for that precise resonant absorption when HF matches the Zeeman splitting. The exact field and frequency tell you at the electron's environment. It's incredibly sensitive to the local chemical surroundings of that unpaired spin.
And then there's MRI, but that's not electrons, right?
Correct. Magnetic resonance imaging uses the spins of atomic nuclei. usually hydrogen protons in water molecules in the body.
But the principle is the same.
The fundamental physics is identical. You use a strong magnetic field to split the nuclear spin energy levels, hit them with radio frequency pulses at the resonant frequency to cause flips, and then listen to the signals as they relax back.
And the relaxation times, T1 and T2, tell you about the tissue.
Exactly. Different tissues, fat, muscle, brain matter. Tumors have different water contents and environments, leading to different T1 and T2 relaxation times. A computer reconstructs these signals into detailed 3D images.
All without ionizing radiation, which is amazing for medical imaging.
Truly revolutionary.
Yeah.
And it all stems from understanding and manipulating those tiny spin flips.
And looking ahead, spintronics, quantum computing.
Yeah, these are really exciting frontiers. Spintronics aims to use the electron's spin, in addition to its charge, to carry and process information. Think spin up as 1 and spin down as 0.
Adding another layer to electronics.
Potentially leading to faster, smaller, lower power devices. And in quantum information, the electron's spin state is a natural candidate for a quantum bit, a qubit. Controlling and reading out individual electron spins is a major focus for building quantum computers.
Using that subtle quantum flip as the basis for calculation.
It's all about harnessing these very specific quantum properties.
So this deep dive, it really shows these two effects. Photoelectric and spin flip aren't just, slightly different outcomes. They're fundamentally distinct quantum dances.
Different choreography, different music, different partners.
Right. And they showcase the dual nature of both light, with its electric and magnetic parts, and the electron, with its charge and its magnetic moment.
Each interaction picks a different handle on the electron, leading down completely separate paths.
So for you listening, understanding these differences isn't just, some abstract physics exercise. It's the bedrock for how we learn to selectively poke and prod matter at its most fundamental level.
It lets us choose our tools: high-energy photons to eject, low-energy resonant photons to flip spins.
Makes you wonder, doesn't it? What other subtle quantum interactions are out there? What other handles on matter might we discover and learn to use? Thinking about things like quantum computing. Mastering these delicate dances feels like the key, right? What incredible things might we build next?